Hello everyone. Today we'll learn about gradient descent, which is a basic topic about machine learning. This is used basically on linear regression to fit the line perfectly. Suppose if there is any data like in this way, and if we try to fit through a line to minimize the loss, this gradient descent actually help to derivative and perfectly optimizely find the perfect line. uh, Definitely we'll evaluate everything in practically rather than read theoretical things. So linear regression basically works on continuous values or such as price is etc. So if anything like x-axis in this area and we are trying to predict y through this x-axis, so if something any point here, so the y predicting y will be this. So let's move on next. So derivative is the thing of gradient. So that's the thing for recall the gradient derivation. So here you can see a normal curve and try to derivative, and here 2 point both at the same point likely. Okay, so this is the negative as tangent line, so that means it's downing blow, and this is the positive tangent line, that means it's upping. Okay, and here we can see a basic function. If we evaluate that, yeah, we will get the same curve, and if we derivate its first derivative, and if we will get a curve like this, and -4 is the where it's below, and 3 is the where it's upper value. You can see here, it's just for recall the derivative. Okay, gradient descent. Two or more derivatives of the same function are called gradients. So that means any function, if we derivate its two or more times of this same function, it will be called as gradient. We will definitely learn in depth of gradient descent. This is basically an algorithm which used gradient to descend to the lowest point of a loss function. It's basically a loss function of linear regression. Okay, so suppose we have data point like this, and this is the linear regression is basically fit the line. But how we human eyes can easily draw this line, but in computer doesn't know how to draw the perfect optimal line to minimize the loss. So computer basically try in this line, this line, this line, this line, this line. So here you can see predicted height, which is our y predicted height, but through our weight. So weight will be multiplied by intercept plus slope. This line is basically for intercept, and the slope is the angle. Okay, later we will definitely evaluate perfectly. This is least square method. We don't need to learn about this. Later, if need, we will come back here. So intercept plus slope into weight. So this is our intercept and this is our slope. Somehow we got this, and this is weight. Let's apply our real data on this equation. So at first you see our first data is 0.5 where weight, and its height is 1.4 actually. Let's apply this intercept, slope and weight 0.5 at our first data. If we do like this, we will get the answer 0.32, and that is here, but our actual answer is 1.4. So this is our gap between our predicting answer if the line is this and our actual answer is this. So we have to residual, we have to find the residual because our actual answer is 1.4 and this is the predicting answer if the line is this. So the gap between this is 1.1. So this is our error for this data, and if the line is this, we have to minimize this error to make line more closer to the point, and at the same time we have to consider all the point and make the error less. Okay, at the same way we have to apply all data point 2.3 2.9 respectively. We will get for second data 0.4 difference, you see very little, and this is for far more 1.3, and we have to do sum of square residual and we will get 3.1 is the total error. If the line is this, the total error is this. Okay, so now make a graph in this way. In x-axis is our intercept and y-axis is our intercept value. Sorry, error. Sum of residual error. Okay, so when our intercept is 0, we are getting 3.1 here. And in this way, if we increase intercept 0.2, 0.4, 1, 1.1, so we may get like this eventually. Let's see. Yeah. So for when it was 0, the line of intercept, and the error is this. When it's likely 0.2, we are getting this. When is 0.4, we are getting this. When is 0 point something, we are getting this. And when it's 1, we are getting the best line, which is the less error from it, and it's almost over the line. And when we are drawing any more line upper to 1.2 something, we are getting the higher error, then it's getting far more away from the line. So in this way we are fitting the perfect line on the linear regression. Hope you understanding. So this is our actual problem. We are stepping into a constant number. In this case, if the actual answer was 0.98, so how we could achieve this? Because we are stepping it from 0.2 ratio, 0, 0.2, 0.4 in this way. So if the actual answer was something like on 0.97 or 1.01, so definitely we will losing the actual lowest error line, which may in this way. Okay, so this is the actual problem we are gonna to fix through gradient descent. Hope you are understanding. So of the point that we are calculating for the graph, this one is the lowest sum of square residual. So this. So gradient descent is basically in other words, gradient descent identifies the optimal value by taking big step when it's far away. That means if our first value error is here and it's likely 3.1, it's a huge error, very big. So we can step in very big, not 0.2. This gradient descent equation and formula is in such a way it's set, it will jump far more when its error is very high, and on the other side it's stay very closer when the error is very small. So if error is higher, it will stay more, and if it's closer to the answer, to the lowest error, it will stay very small to don't miss the actual answer. Okay, so For this, we have to do the derivation of our sum of square residual equation. Which equation is here for our first data, second data, and third data. So if we do the derivation, we will get this two here, and this is the derivation after we get to derivatives d by d intercept in okay. So if we do d by d intercept derivation, then we will get the curve such in this way, and this integrate is the jump. When it's very very higher error, it will jump for more, and when it's slightly closer, it will smaller, and when it's more likely, it will more smaller step. When it's more closer, it will more smaller step to move. So let's see. When the intercept is 0 intercept, then error is 3.1, and that is very huge difference, one bit from 0 to 3.1 minus 0. 3.1 is the gap actually. So here is another thing. We will get the value if we take 0.0 as intercept. We will get the value from the intercept, and we have to apply a learning rate with it, which is 0.1. In computer we are taking 0.11 0.0001 more smaller, but in learning purpose we are taking only 0.1 to make it easier. How accurately we are trying to make the result. Okay, so we have to multiply it and we will get it. So we have to find the new intercept. Our old intercept is 0, so we are putting here a new intercept. Here again, it's look likely Newton-Raphson or simple iteration method, you know. So the new formula is old intercept minus step size. This is step size is the derivation answer into learning rate. So we will get the positive 0.57. Okay, so again we have to put here this one again. So we will so this is our second, and we will get this sorry, this is our second intercept value, and second intercept is likely getting this more closer here. So again when we put this second intercept value, we are more closer to the answer, and now if we multiply it to the learning rate, we are from 0.57 to 0.8. It's not too much than first 0 to ether. It's slightly more smaller here and here, you can see. So in this way gradient descent formula is set up. It's big jump, it's smaller jump, it's so smaller jump. In this way it's will stuck in here to find the more optimal and don't miss. Okay, so basically this is the gradient descent actually. But there are another thing which is slope. I somehow told you the slope is 0 point something. That's the reason we are coming here to the answer. But in real life, how you will get the slope? I told that's the reason you got. But if I didn't told you the slope, how you will get come to the answer. So here is two unknown thing in our equation. One is intercept and another is slope. So we have to derivate both of the thing to find our sum of square residual error and find these two more optimal. So basically there are two things, and this is the actual answer, 0 or closer to 0 error. This is intercept and this is slope. Both is trying to trying to get closer, more optimal in this way. How we do this is 2D. This is 2D because we are working only in respect of intercept, but in real life there are many dimension, but in this equation there are 3D because intercept and slope. So this is 2D xy, sorry, this is 3D xyz. This is likely our curve, but this may occur in very deep in here, or any frontal this way. So that is actually slope. It's indicate angle. So that means slope is basically, if we take example, okay, let's draw here. Suppose some data like this, we can do any good line in this way. If we can do in this, try in this way in different angle, that can be more optimal line. So this is the actual slope, how angle between of that line intercept. So in this way we have to derivate two things. First dy dx through intercept respect of, and another is derivation respect of slope. So simultaneously we will do both in a thing to find those both unknown value at the same time. Okay, so this is the formula. All squares comes to here, and others calculation, we don't go to the depth of derivation because it's you should know the derivations basic. Okay, in the same way, when we will do that, let's try to visualize. At first our our intercept is 0 and slope is 1. That is basically take in general. So when intercept is 0, this line actually, when intercept is 0 and the slope is 1, so we'll get far more away. But when after calculating, our new intercept is gonna 0.016 and our new slope is gonna 0.008. That means a bit away angle. You can see difference between here and here, a bit angle upper side. So it's at the same time it's find the perfect intercept, and at the same time it's calculating the actual angle between the intercept to the to fit it's actually. So you can see the example here. Every line try to fit with its least loss. Okay, so eventually it will get the perfect line whose loss is very minimum. So this is actually visualization, and there are many more losses functions. So this was our actually gradient descent. Hope everyone understand well. If we finalize it, let's draw. If we have any data like this is our data point. In real life there are various odd case, so we are not doing in constant rate in gradient descent. We are doing, when we are here, we do a very long step, and when we closer to answer we do very small step, and this is done by the derivation. And at the same time we are not doing only the same angle line, understand, we are doing the line also the angle of how it will be the most minimum loss. Okay, hope everyone understanding, and thank you so much for watching this video.